So our discussion last time was Laplace's equation for one dimension. I'd like to look at properties of this solution for 2 dimensions and 3 dimensions, and we'll stay in the Cartesian coordinate system. So what does it look like? For 2 dimensions, we add another term in the differentiation, and so we have second derivatives with respect to x and y, and for Laplace's equation this is equal to 0. For this equation here, there's no simple general solution, but for many situations, given certain boundary conditions, we can find solutions. The boundary conditions are usually in terms of values of the potential on a closed boundary, so it can be a square, rectangle, circle, or an ellipse, for example. The solutions are more challenging to obtain. We'll look at a couple solutions later to see how one goes about doing that. For 2 dimensions, we can make similar observations that we did for 1 dimension. So remember, here we have no z-axis. But we have a v, x, and y, and it's the solution to the 2-dimensional Laplace's equation. We can use the fact that averaging over some line integral, we'll be able to find the potential at the center of that region. So if we take a circle of radius capital R and integrate the potential around that circle, we will get the value of the potential right in the center of that circle. So I show that over here. We have a circle drawn in space where we have no charge. It's defined in terms of the origin here. We might have a point charge here creating the field, or we may have some other surface creating the field. Important thing is that if we go back to our funny R definition, which is this quantity right here, this is a vector that points from the origin to a point on the sphere, then we can write that in terms of the law of cosines, r squared plus capital R squared minus 2 little r capital R cosine theta, and those angles and dimensions are shown here. The value of v at the point P at the center of that circle, and the circle is defined by this capital C capital R. The circle is of radius r and it's centered at the point P. If we average then the potential over this surface, we'll get the value here. Well, that's of use, for example, when we're using the relaxation method, which we'll do later. The second theorem is that by the same reasoning that we used before, having these second derivatives equaling 0, there can be no local maxima or minima within the region. You can only have maxima or minima at the boundaries. Laplace's equation yields somewhat boring featureless solutions because of the fact that it can't have max or mins. So in other words, there's no bumps and no valleys. In terms of what it looks like in Cartesian coordinates, for example, if you had a boundary where this side of the, let's say this box here, was at a potential v0, so that's up here, as soon as you go to the value of x and y where you get on these regions here, it goes to 0. So it's 0 here, 0 back here, and 0 here. If you were to take a rubber sheet and stretch it over a frame that gave you those same potentials, in this corner here you just have an infinitesimal distance that would take you from v0 to 0. This would fall very quickly. This is the solution to Laplace's equation. It's actually a very good approximation. So if you put a ball on the surface and just let it roll under gravity, it will roll, of course, down the hill in any direction. So if you're over here, it will roll this way. If you're in the middle, it'll roll right down the back of this potential. It will be like a charged particle, where this now is the electrostatic potential. If it were positive, it wants to go to smaller potential. So it will roll, the particle will move, if you were to let it go, in the same way that the ball on the rubber sheet would roll. So that's one way of thinking about how these solutions are going to look. So in 3 dimensions, again, we just add one more term, Cartesian coordinates, set that equal to 0. Again, there's no simple general solutions. The value of v at P now is the average over a spherical surface, again of some radius, capital R, centered at the point P. So let's go back to our picture then. We have a point P and a surface S that's made of a sphere of radius, capital R. If we take the average of the potential over the surface, how do we do that? Well, we integrate the potential over the surface, where this is the surface element on the surface, S is the whole spherical surface, and then simply divide by the area of the sphere. So I think you can see that this is a two-dimensional average over the surface of that sphere. I should say three-dimensional, excuse me. So then let's take a simple case. So consider 3D potential due to a point charge. We're interested in the potential at the point P due to this charge in terms of this average value. The vector r points from the origin to the point P. The length of that vector is the scalar r. Okay, so what we're trying to do here is calculate the average of the potential generated by a single point charge q, right here, located at the origin, over the surface of a sphere surrounding this point P. We're going to take that to have a radius, capital R. So another sketch of that is right here. Here's our point charge. Here's the point where we're interested in the potential. The theorem says that if we take the average over this surface of this sphere, we will get the potential at this point. So here's the area element. Obviously, we're going to be using this distance here to define the potential here. So it'll be a function of funny r. If we write that in terms of r theta phi, if you remember, the surface area element on the surface of a sphere is the radius squared sine theta d phi. And remember, phi is just going to be integrating over this parameter. There will be no phi dependence on funny r, so that'll just give us a 2 pi. The potential at the position defined by funny r is this quantity right here. It's kq over the funny r distance. So here's the point charge, and we're talking about the potential right here, and that depends on funny r. So what's the average? Well, the average, as we said before, is 1 over the area of that surface times the integral of the potential at the position funny r times the ds at that position funny r. Well, the surface area is very simple. It's just 4 pi r squared. So we put in our potential. kq here is this kq. We're going to have our d phi and d theta here, so we're going to have to integrate over phi first, 0 to 2 pi, which will just give us 2 pi. That's this 2 pi here, by the way. The theta dependence of all the argument, of course, will mean we have to do the integral with a little bit more complex quantity here. What is that? Well, here's the r squared sine theta from up here in our area element. And then 1 over funny r is given by the law of cosines, which we've already discussed. And so that's this quantity right here. So it has a scalar r, and it has the radius of the sphere, and has the theta dependence here. Removing all of the constants and bringing them out here, I think you can see that this is going to be something like q over 2. Everything else will cancel. Let's see if that's right. We want to keep the k, excuse me. So it'll be kq over 2. Everything else cancels. Then here we're left with this integral right here. Well, it looks complex, and it is, but either you use brute force and do the integral, or you use Mathematica. And so over here I show you the results. Remember, if we make a bunch of assumptions that clarify things that are real and things that are greater than 0 and so on, then the integral is found very quickly. What we find is that that integral is equal to 2 over r. So I've repeated it down here. Here's the integral. That's equal to 2 over r. So now we can go back and put in our kq over 2 here times 2 over r, and that'll just give us kq over r. So if you come back up here to look at what the potential is at this point due to a point charge, we know that that is in fact kq over the distance little r. What we've done then is shown that the theorem, which is given here, that the value of v at p and so on is given by the average of the potential on that surface divided by the area. That is the average. Then we get the potential at p from Coulomb's law is kq over r. We've shown this, that the average of v funny r over that surface is kq over r. For this particular case, then, we end up with the same result, that v at the point P is in fact the average of the potential over the surface of a sphere that surrounds the point P. The second part of the theorem is like the 1 and 2D case. There can be no local maxima or minima within the region. So maxima and minima can only occur at the boundaries. In 3D, I don't know what you'd call it, there's no black holes. There's no bumps or valleys, so to speak, in the three-dimensional space. The consequence is you cannot trap a charged particle in a free region of space surrounded by charges or charged surfaces. In order to form a minimum, you would have to form a trap, a minimum in 3 dimensions in that space. This statement that a charged particle cannot be held in stable equilibrium by electrostatic forces alone is known as Earnshaw's theorem. It has most significance in a 3-dimensional space. Here it is repeated. I just wanted to point out, this is in 2 dimensions actually, that saddle points can be solutions. They're unstable in one direction. So I show you one here. Consider this function here. This function satisfies Laplace's equation. It has a saddle point at the origin. So if you plot the potential, it looks like this right here. This is the origin, which is at 0, and it has a minimum in this direction and has a maximum in this direction. So you could say then that it's stable. It looks stable in this direction, but you could imagine that it'd be impossible to keep it directly on the ridge of this structure here. There would always be a tendency to move back and forth this way, and as soon as it does, then it falls. So if it's rolling down here and it just starts moving over this way a little bit, then instead of hitting the origin, it would come down and then fall down here and then maybe like that. It's unstable in one direction and therefore would not be able to be trapped. If it's a solution to Laplace's equation, there can be no min or max. There can be a saddle point. Therefore, you have no way of trapping that particle. One way to look at it are the forces. The forces are equal to minus the Q, so let's call that a capital Q, times the gradient of the potential. So for this particular potential, the x direction has a gradient equal to dv dx with a minus sign will give us a force, and the same for f sub y. So putting in our potential, we end up that the force in the x direction is minus 2qx, and so any motion to a larger absolute value of x is opposed, so that it looks stable. And that's what I said before. It'd be a well in this direction only. If you take the y, it's the opposite. It has a plus 2qy for the force in the y direction. So that means that any motion to larger absolute value y is assisted, so it would be unstable. What that means is that if you move any direction to larger value of absolute value of x would be this way or this way, it's unstable and you therefore cannot trap the particle. Same would go for this potential here. Let's suppose you just had 2 point charges, let's say plus q, and you put another charge right in the middle. Well, you know that this one would push it this way, this one would push it this way, so right in the origin you'd have 0. And so you could imagine that you would have a stable equilibrium in this direction. If you look at the surface that you get from just adding these 2 potentials from 2 point charges, you end up with a saddle point again. You will have the same problem with the forces giving you stability only in one direction. Because you cannot stay exactly at one point, you'll go out of equilibrium. Well, I just wanted to mention there is a way to trap particles, charged particles, in 3 dimensions. And so if you have this volume V and these surfaces here, you could quite easily find the potential inside this 3-dimensional volume. The surfaces are these curved surfaces that you see here. It's not really a partial sphere, but you might think that way, and for this surface here, and then you have this hyperbola that's been rotated to give you this surface here. So what you can do is put DC voltages on these potentials such that a particle would be trapped along this axis here. But in order to get stability, you have to vary the potential in time back and forth. So the particle starts to go out of equilibrium, gets pushed back, and so it basically forms a very small oscillation right in the center of this trap. To find those potentials as a function of time is not very difficult if you can do the Laplace's equation in 3D for these surfaces. So let me repeat. Suppose you just call this the potential V1, V2, V3. Solve Laplace's equation. Then what you can do is just let one or more oscillate as a function of time. This does not violate Earnshaw's theorem because you don't have electrostatic conditions. So you're using both DC and AC electric fields, and this structure right here can actually be used as a mass spectrometer, because if you have a single charge on a particle, the stability depends on the mass. The inventor of such an electrode structure was Ernest Paul, and he's a Nobel Prize winner for this type of devices that he made. He made several other types of mass spectrometers using electrostatics and oscillating fields.